I'm Andrea Marin, and I'm here with Alessandro Abate, the other chair of KEST. And it's a pleasure for me to introduce and chair this session, and where our keynote speaker is Professor François Bachely. And François Bachely has a research interest that include a lot of subjects like applied mathematics, probability theory, stochastic geometry, dynamical system, and communication, network science, information theory, wireless networks. He's co-author of several research monographs on network mathematics, including point processes, queues, max plus algebras, and the network dynamics, stationary queuing networks, stochastic geometry and wireless networks, point processing and stochastic geometry. Those are very well-known and appreciated monographs that probably many of us has read. He received the France Telecom Prize of the French Academy of Sciences in 2002 and the MathX Award of the Simons Foundation in 2012 and the SEM Sigmetrics Achievement Award in 2014. He also received the 2014 Rice Prize and the 2014 Abram Prize Award of the IEEE Communication Theory Society for his work on wireless networks, stochastic geometry. He is currently the principal investigator of an ERC project on mathematics of networks at the INRIA of Paris. He held the Math+X chair in mathematics at the ECE at the University of Texas at Austin between 2012 and 2021. Before this, he held a position at the INRIA, the École Normale Supérieure, and the École Polytechnique in Paris. He's also a member of the French Academy of Sciences. Today, he's giving his talk on stochastic geometry-based performance analysis of wireless network. I would like to thank François for accepting our invitation, and I let him to give the speech. Thank you, François.
Okay, so can you hear me okay?
Yes.
It is good. Okay. Well, first, I would like to thank you for your kind invitation. It's a great honor and a great pleasure to give this lecture. Actually, this is really my community, the performance evaluation. I mean, the part. I mean, I was in my PhD time a queuing theorist of some kind. And actually, I will explain in my lecture how from this interest grew a different line of thought, which is based on spatial point processes. Okay, and so I will describe about 20 years of research, and it will be a sort of technical talk. But I will give a high-level view of this research. Okay, so let me share my screen. If it works again. Okay, start broadcast. Okay, and now I hope you see my tablet. And okay, do you see my slides? Hello?
Yes.
You see the slides. Okay, very good. Thank you. The title of the talk indeed is Stochastic Geometry-Based Performance Analysis of Wireless Networks. And I will cover 5 topics. One on Poisson stochastic geometry, the sort of basis. And then I will go to this sort of 20 years of research by looking first at device-to-device networks, then at cellular networks. And this first part will be about static stochastic geometry, and I will go more to dynamical aspects, first for D2D, device-to-device, and then for cellular networks if time allows. Okay, so what is Poisson stochastic geometry? So it's a very rich topic. There is a very beautiful book that I strongly recommend. Initially, it was Stoyan, Kendall, and Mekker. And there is a fourth author who joined in the last version, which is a very, very recommendable book, very nicely written. Okay, so I will describe spatial Poisson point processes, spatial short noise fields, which will become interference very soon, and Voronoi tessellations, which is a principle of connection to the closest. Okay, so a point process, I mean, I won't be very formal, but I want at some stage you understand a part of the intricacies, mathematical intricacies. Spatial point processing on R2 is a random, finite, or countably infinite collection of points in R2 without accumulation, okay? That's a space of realizations. And one can think of a realization of a point process, generally speaking, either as a collection of points without accumulation, countable, say the set Ti, the set of collection Ti of points. Every Ti is an element of R2. And one can also see that, and it's very fruitful as a random measure. So it lives in the space of counting measures, which are sum of Dirac measures at this point Ti, right? And so when I write integral of f of t phi dt, where phi is the measure, is nothing else than the sum of the f of Ti. Okay, so it's a good space, and you can put probability on that, and that's a theory of point processes. The only point process that we will use, at least at the beginning, is the Poisson point process. So we, of course, in performance relation are very familiar to it with it on the line, but we will need it on space now. You take lambda, any locally finite measure on R2, positive measure or non-negative, right, and non-null. And you say that phi point process is Poisson with intensity measure capital lambda if the chance to see n1 points in A1 and nk points in AK, where the AI are disjoint sets, is nothing else than the product of Poisson laws of parameter lambda of AI. Okay. So, of course, it's a classical thing on the line, but in space, it's exactly the same. It exists. It's a beautiful object, and it has an incarnation as a stationary point process when this measure is lambda times Lebesgue measure in R2. Okay, so it exists, and it's very useful, partly because of the knowledge that we have of its Laplace functional. So the Laplace functional is a sort of generalization of the Laplace function. So it acts on functions. You take phi, f, a non-negative function, and the Laplace transform of the point process phi at f is defined as the expectation of the exponential of minus f of x phi dx. Okay, so linear operator, as you know, on the space of measure is corresponds to integrating that measure against a function. Okay, and it turns out it's an easy exercise that the Laplace functional of Poisson point process of intensity lambda has this form that you will all believe in if you have not seen it in space, because it's just a generalization of the Poisson law. Okay, you recognize e to the minus 1 minus z times theta, right? If it were a Poisson law. So it's a slightly different form. Now it acts on function, and it will be instrumental in the evaluation of interference created by transmitters located at a Poisson point process. Okay, so this is the setting. Next object, which is fundamental, is the Poisson-Voronoi tessellation. And you have a picture of it here, and you see the Voronoi tessellation of a Poisson point process in R2 here. And one defines a cell associated with each nucleus or points or atom of the point process, say TE, which is the set of all locations of the plane which are closer to this atom T than to any other atom. So you see a set of half-plane conditions. It leads to a convex polyhedron, which is depicted here. And these are the parts of space which are closer to this nucleus than to any, right? Okay, so it's also a classical object. And the beauty of it, it's quite computable in the Poisson case, because of the famous empty ball criterion, which was already in the paper of Voronoi and Delaunay, that a a point of the Euclidean space X belongs to Voronoi cell of nucleus capital X in phi, if and only if the open ball of center small x and of radius norm of small x minus capital X is empty of points. Okay, I just say that capital X is the closest to me, right? That's if I'm small x, right? That's a very simple principle, but you can leverage that in the Poisson realm by using the Poisson law, right? So X belongs to the Voronoi cell of 0 if there is an atom at 0, if and only if the ball of center X and radius norm of X is empty of points, the open ball, right? Which is nothing else because of the exponential formula of the Poisson law as X of minus lambda a ball of center X and radius X, right? Norm of X. So it's a very fantastic principle because it leads to this concept of connecting to the closest in the Poisson world as something computable. Okay, so that's all what I will say about these mathematical foundations, which are classical. And I will start with Poisson device-to-device networks. Please interrupt me anytime, of course. I don't see any chat, so you have to prompt me by questions, right? Okay, so the realm this is a line of thought that we started with Bartek Flasichin, my colleague at INRIA, in 2001. So that's why I say it's 20 years of research. And in a series of papers that led to a book in 2009. And this model is the dipole model, the Poisson dipole model that we introduce. I will give the Poisson-Shannon formula. I will discuss the property of coverage and the distribution of Shannon rate. Okay, all these things will be defined. Okay. That's the Poisson dipole model. Let me zoom in. I hope it works. Okay, so you see small dipoles, which are these black directed segments on the picture, and each segment in this simplified model has length r, small r, a random orientation, say uniform, is isotropic, taken at random. The initial point is the location of the transmitter of this link, of this dipole, and the black point is the location of the receiver of that link, right? And you see features, I mean, the small segments that are located up at the transmitters, which represent antennas. And I depict here the situation where we use Aloha, namely every transmitter decides willingly to toss a coin to be either silent or to transmit, right? And the red here are those which transmit, and the green are the silent ones, right? E is equal to 0, that's the coin toss for each, right? Okay, and okay, so that's these are the device-to-device communication. Every device has its buddy, its friend, communicating with it. Of course, you can extend that to variable R, variable orientations, and okay. So, but it's a natural model. And the Poisson-Shannon model under Aloha features a set of transmitters. Something which one called fades, which are come from propagation. I will not describe them in detail, but they are very important in wireless communications. A path loss function L of dot, which gives the attenuation for the given distance, right? The Aloha coin toss. This will be a slotted model, and it's in this slot, reference slot for transmitter I, it will decide to transmit or to be silent according to the 0,1 valued variable EI, right? And then you can assess what is the interference seen by locus Y in the slot as the sum, assume the powers are 1, of those which transmit EI, right, times the fading from locus I, transmitter I, to locus Y, the observation point, divided by the attenuation, right? And the attenuation comes from the from physics. I mean, it's conservation of energy, multipath, and things like that. Okay, so it's a function that decreases to zero with distance very fast. Typically, like if it were the free space, it would be it would be R2, right? It would be the distance squared, just back in the plane conservation of energy. Okay, but it's usually decreases much faster. So typically models due to reflection on the ground like R to the 4. Okay, and a receiver active at 0 in the slot will be covered for the constant bitrate model for threshold T if the signal to noise and interference ratio exceeds threshold T. And this SINR, a very fundamental concept coming from Shannon's channel coding theorem, when you treat interference as noise, to check whether you can achieve a certain bit rate, you have to, in the Gaussian noise case, to just measure the ratio of the power received by the sum of the thermal noise power N and the interference power created by the other transmitters, right? And so what you see immediately, what you see, the definition of I phi, the interference for phi, filtered by E, you see it's a shot noise. It's the integral with respect to a certain function, which is 1 over L of the distance, integrated with respect to the point process. Therefore, it is computable through our Laplace transform formula. And that's what we understood in this early work with Bartek. And we could call that the Poisson-Shannon probability of coverage formula. If phi, the set of transmitters, is a Poisson point process with intensity lambda in R2, so homogeneous translation invariant. If the EI are IID with probability of transmission of equal to P, that's the ALOA parameter, then phi E is a Poisson point process with intensity lambda P. This is a classical result. And if the Rayleigh, if the fades are IID Rayleigh, which is a classical model coming from propagation theory when there are multiple reflectors, namely the powers received are exponential with mean 1 over mu, then the probability of coverage can be assessed very quickly because you see this function Qt of R lambda P is the chance that the fade stemming from the transmitter exceeds, so the fade divided by L of R, that's the L of R is the distance to the, so that's the signal power received from the intended transmitter, from the transmitter of the link, divided by L of R exceeds, divided by N times I phi, plus I phi, the, you recognize here the signal to noise ratio exceeds T, can be rewritten as is written in the middle of the page here. And then you use the fact that N is a constant and F is an exponential to recognize in this the product of two exponential function. There will be e to the mu TL of R times N times the Laplace transform that is computable of the interference received at the origin, say, at the point mu T L of R, right? And so when you express the fact that that the fades are Rayleigh, you get a closed form expression, which is in terms of an integral, which is, as you will see, computable in special cases. But this is the essence of it. You see, it's very simple. Just integrating into this very simple geometric setting the Shannon formula for the Shannon rate formula coming from the channel coding theorem. Okay, So that's the principle, and it receives two interpretations. This calculation, you can say first you take a tagged user or a tagged receiver. You would take this guy at random in a big ball and look at this guy, and if the ball is big, and pick this guy at random in this big ball, then this is the chance that this guy receives. I mean that's its SINR exceeds t. Okay, so therefore you can get transmission at the sub-prescribed rate, log of 1 plus t, right? Okay, it has another interpretation also as a spatial average, like in queuing theory. It's also now in space. If you take this large network of transmitters, you take a big ball and you look at the large collection of links. There's a fraction of links which can transmit at this rate log of 1 plus t, right? Okay, so this has these two interpretations. So like in queuing theory, there are lots of interesting spatial cases. So the most interesting case which we studied first was the power law path loss. L of r is r to the beta. You need beta to be more than 2. Otherwise, you are burnt by interference, which is infinite, because you're on the whole plane, right? But beta is always more than 2 in practice, so typically 4 in urban areas. And if you look at the interference limited case, n is equal to 0, then these ugly integral formulas boil down to very simple shapes. So you see, for instance, in this interference limited case for the path loss r to the beta, qt is nothing else as exponential of minus lambda p times r2 times t, this threshold to the 2 over beta, times kappa, k of beta, where k of beta is now famous constant, which receives a name of a spatial wireless contention constant that gives this multiplicative term that shows up in this exponential, right? So, and these are extremely simple forms. So it's a 2 pi 2 over beta sine 2 pi over beta. Okay. That's just computational, but what is interesting is to look at what it, so let's look at this one first. Okay, this is, so you see the points, which are the transmitters, and you see in different colors the set of the region where a receiver located in this region would indeed receive above threshold t at a rate more than log of 1 plus t, right? So, and of course, I mean, these are dependent regions. These shapes interact a lot, and they are not even connected. And in this simple formula, you connect and cover all this type of complexity. So this is the shape that you would get if there would be no fading. And if this is a point-to-point relay fades, this would be a picture of what you see in this D2D network. Okay, so there are lots of things that you can do. I mean, you all certainly played in one class or another with the Aloha optimization. That's the spatial Aloha optimization. You can also ask the question, what is the value of P, the medium access probability that maximizes the spatial density of coverage for dipole distance R. Since you get the closed form, you can, very generally speaking, express this optimal policy in closed form. This is a quite general result, which holds for all function, attenuation function, and thermal noise. In the special case where you have this power law path loss with parameter beta, it's even simpler. So this density is inversely proportional to the square of R, the distance of the links, the length of the elongation of the links, inversely proportional to the t to the 2 over beta. So you know the beta is more than 2. And you see this famous constant k of beta showing up in the formula. And so, I mean, you can do the same type of games, of optimization games that one does on wireline networks, right? With Aloha or Ethernet. One can also compute the distribution of the Shannon rate. So it's the same principle, which in a sense, we just computed the CDF of this Shannon rate because we looked at the chance that it exceeds, that SINR exceeds T, right? But you have to work a little bit to look at either the expectation or Laplace transform at point S of the Shannon rate that the typical link gates for a distance r, and you get again either integral expression or closed form expressions with again the same interpretation of either being on the typical link or being a special average of the say Shannon rate that the user gets, right? That the receiver of a link gets. Okay, very good. So there are lots of, I just give the principles. There are lots of extensions. You can go beyond Rayleigh phase. You can go beyond power law path loss, which is very important. Perhaps an observation that I should make right in this formula. Okay, let's see. Or perhaps I will go to that a bit later, right? So sorry. Okay, you can look at a lot of game theoretic spatial things where you adapt the ALOA parameter to either globally to maximize, as we did, the spatial probability of success or spatial coverage. But there are also game theoretic ALOA versions, which we studied, which are quite interesting, but I don't want to enter into all these intricacies. And I want now to go to the cellular case, which was really the start of the wide use of this viewpoint, right? And we have two papers with Jeff Andrews at UT, and he was a postdoc at that time, Radhakrishna Ganti, who is now back to India at IIT Madras. But really, I mean, so D2D are just toy models, and they represent, say, mobile networks, but really the big industry is in cellular. And I will explain how we adapted what we did with Bartek, with Jeff and Radha, to the cellular case. Okay, so there will be first the Poisson-Voronoi setting, then the Poisson-Voronoi-Shannon setting, and that's for the single tier, and then I go to multi-tier. Okay, so the picture goes like this. You have base stations now, which are these towers that you see in cities or in the countryside, which are arranged according to homogeneous Poisson point process. So you will have a good question to ask whether it's justified, and we'll explain in the answer that in a sense, yes and no. But that's for the simplest model what we took at the beginning, and users are also located according to some independent stationary point process. And you see here that each user is served by the closest base station. And so it leads to connection to the closest, the Poisson. If the base stations are Poisson, then the users really connect according to schemes which are depicted on the left. You see the connection and the links, which are the potential links between users and base stations in this Poisson-Voronoi tessellation, right? And so it makes sense because you'd better connect to the base station which offers the best signal, right? That's the principle that people use in wireless communication. Okay, and then we go the same path. We look at the SINR experience by the typical user. The signal stems from the closest base station. Interference is created now by all base stations outside the Voronoi cell of the tagged user. There will be a thermal noise. Shannon rate is also the Shannon channel coding theorem, proportional to log plus of 1 plus SINR. That's when you treat interference as noise. And the question is again, what is the law of the Shannon rate offered to the typical user by this cellular architecture? And so we asked ourselves this question in 2010 with Jeff and Radha, and here is the answer. Again, I will give it in the simplest case. Path loss is R to the beta. Fading will be a bit more general. Fading from the base station will be Rayleigh with mean 1 over mu, which 1 over mu can represent the transmission power plus the Rayleigh fade itself. And fading from other base stations will be with a representative F with general distribution. And in the special cases, it will be Rayleigh as well with the same mean. Okay, you can assess coverage and Shannon rate in a similar way. And again, you ask the question, what is the chance that a typical user has a SI norm more than T? And if you get that, this is the PC, probability of coverage at T lambda beta, then you are done with the distribution of Shannon rate by classical manipulation, right? Again, same interpretation. This probability will be the average fraction of users who achieve a SI norm more than T, or the average fraction of the network, of the area of the network in T coverage, right? So that's the idea. Okay, this is the Poisson-Voronoi-Shannon formula, which states that this probability of coverage has a very simple form. So you see it's an integral of an exponential function. There is you integrate the dv. There is a linear term e to the minus pi lambda v kappa of t beta. Kappa is a constant, and there is a term which, for instance, would be quadratic if beta is equal to 4, a Gaussian term, which has multiplicator mu t n. N is the thermal noise, right? And kappa is this constant, which involves the incomplete gamma function. And there is an expectation. And you see F is the representative of the fading from base station other than the closest one. So F is a random variable. And you see, for instance, that you take the incomplete gamma function with the second argument, which is random. That's why there is an expectation. And this is multiplied out by F to the 2 over beta, right? Okay, very good. So this is and so what is interesting is not the formula, although the formula is important, you will see why. But what is nice is the proof. That's the only proof we'll detail a little bit to explain why you really can call it the Poisson-Voronoi-Shannon theory. It's a formula. So the chance to be covered at T is the chance that the SINR is more than T, and you will condition by the distance to the closest base station, right? So it's also a Rayleigh distribution with parameter lambda pi. Okay, so it's a classical thing. It's an empty ball condition that you can differentiate so that the density of the closest base station for the typical user at the origin. Okay, and now given that this closest base station to you, user, is R, your SINR is the fade from the closest base station times R to the minus beta divided by N thermal noise plus IR, where IR is the interference outside a ball of radius R. Because you know that you filter interference in this cellular setting by having a good signal and only interferes outside the ball of radius R, right? And this is the Poisson-Voronoi principle. Here I have just applied twice the principle, Voronoi principle that I connect to the closest. And then I apply the Shannon formula by filtering interference and only keeping that stemming from what is outside the ball of radius R. Okay, so that's already Poisson-Voronoi and Shannon together, right? Then you use the Rayleigh thing, okay? S is exponential, so this chance that S exceeds T R to the beta N plus interference of this type outside the ball of radius R is nothing else against the product of the Laplace transform of the interference outside this ball at point mu T R beta times an exponential function that contains thermal noise. Same game, right? Okay. And now the beautiful thing is that, so you get immediately the formula, which is in red here, which gives you this already the desired form almost. The only thing that you have to do is to compute now, that's a Poisson thing, the interference as a short noise field, right? And you use the Poisson, Laplace transform of Poisson point process to compute this as an integral of this shape, right? Again, an exponential. Now you integrate, because it's a non-homogeneous case, you don't integrate for distances which are all possible distances, but only distances from R, the shots of the interferers outside this ball of radius R. Okay, and then you work a little bit, you plug in what is S, you do a little bit of massaging and elementary calculations, and you get the result. Okay, so what the beautiful idea is is to use the same setting, but to be able to represent the cellular structure by saying that you have only to compute, given where the closest transmitter is, base station is, you just know that there is no interference in a big ball of this radius R, and it's only far away interference that plays a role, right? And this is the essence of cellular architectures, right? Again, same thing, if beta is equal to 4, this is Gaussian calculus, you get closed forms. In terms of Q function, which is the tail of the exponential, if S is Rayleigh, it's even simpler. This term kappa integrates to something which is this black rho of t beta integral, which is computable, particularly in the case where beta is equal to 4, as we shall see. So if you look at the interference limited case, again, n is equal to 0, and you get a constant property of coverage, is also called spectral efficiency, for all densities. It doesn't depend on lambda any longer. It's quite interesting and surprising fact, but it's very much linked to the path loss function R to the beta. And if you mix all simplifications, Rayleigh fade, interference limited, you get this amazingly simple formula that doesn't depend on lambda, and it's 1 over 1 plus square root of t times pi over 2 minus arctan of 1 over square root of t. Okay, so when you think of the complexity of the initial object and the simplicity of the formulas, I mean, this is surprising, but these are, of course, very special cases, but beta is equal to 4 is quite meaningful, and Rayleigh fades are meaningful as well, right? So, okay, so same story. I won't describe the Shannon-Ray distribution. It's also obtained in integral form, but the same story is that you get simple expressions and integral expressions, and if you look at interesting special cases, you get closed forms. Let me say a few words on the multi-tier Poisson cellular network extension. You have several types of base stations, macro base stations with high power, a pico base station with smaller power, and femto, which are even smaller, right, in black. And again, you connect to the closest or to the best signal. Actually, it should be more the best signal, which doesn't lead to Voronoi, but another principle, because here powers are not the same, so it's not Voronoi any longer, but something that generalizes. And the short story is that you can do the same thing. Coverage by tier I. So tier I will be a Poisson point process of intensity lambda I with a transmit power pi and SINR target Ti. You again get a power low pass loss Rayleigh fades, and you say that the tagged user is covered if there exists a tier such that the SINR, it will then be the closest for that tier, exceeds for the closest point to the origin for that tier exceeds Ti, right? So this is the principle. And the same formulas hold. So this is the multi-class Poisson-Shannon Voronoi formula if you want. So Voronoi should be in quote because, as I said, it's not the Voronoi tessellation, it's really the best received power. And there is a closed form expression, again, integral expression, where you see the extension of this formula. Again, you see terms here which are like the norm of xi. You integrate respect to Lebesgue measure at xi. Again, there is the, you recognize the second term, multiplicative term, which is this exponential of the norm of xi to the beta. So something that just generalizes what we did in the earlier case, right? And again, in the interference limited case, there is a very simple formula which is given here for the probability of coverage. And again, if all base stations and densities scale the same way, you get constant spectral relationship for all density. When you densify these networks for the power low pass loss, they are scale invariant. You get the same probability of coverage, right? So it's not at all the case in general. When you look at more other type of pass loss function, which are more realistic, it's not the case. And there is a big literature on that now. Okay, let me skip the extension and perhaps make a small break and give partial conclusions before moving to the dynamic part on this wireless stochastic geometry. So it started about 20 years ago. You represent the position of network elements as realization of Poisson point processes here. All performance metrics which are pertinent and all interaction are based on information theory. And so metrics would be coverage or Shannon rate, interaction as through information theory. Performance metrics are evaluated as spatial averages, and there are lots of tools to do that in the translation invariant homogeneous case. It leads to a system-level analysis of a large wireless network, whatever type, cellular, D2D, a mixture, single type, multi-type. And surprisingly, like in queuing theory, it reduces this system-level analysis, which has a huge number of parameters. If you look at where base stations are, what are the fates and things like that, this spatial average reduces the analysis of this extremely large data set to a very small number of parameters. And so you have seen the arctan function with only surviving a few key parameters of the structure, T, the threshold, things like that. And therefore, it's quite used now for network analysis and optimization optimization, parametric optimization for people in for instance operators, they want to know what intensity of base stations they need in order to have this quality of service, this probability of coverage, this average Shannon rate of this or that, right? So that's how people are using these things now. Okay, so perhaps I will take a few questions so that may be a break before going to the dynamic part.
Is there any questions?
Let me stop sharing. It's about half time, so it's good to to take a few questions for this first part.
Maybe it's better, Francois, if we collect the questions at the end of the talk.
Okay, very good. Okay, then it will make a small break. And so let's go to the second part. Okay, very good. Let me share my screen again. So share content, screen, start broadcast. Okay. Very good. Okay, can you see my screen again?
Yes.
Okay. So all what we did was static, right? Static in the sense that you have these base stations, there are Poisson, there are these users, there are Poisson, and for this static configuration, you compute a spatial average of the, say, distribution of the Shannon rate, right? For the typical user, right? So like in queuing theory, the steady state, if you want, of the system, which is the spatial average, replaces time averages, right? Okay, very good. But these problems are fundamentally dynamical, right? So there are lots of join and leave, motion of users, beamforming, and okay. So power control in the cellular case. In the D2D also has a lot of parametric, a lot of dynamical aspects. For instance, user motion. Okay, and so the more recent part of the research has been focusing on dynamical aspects. I will again try to be pedagogical by going first to the D2D system, which is the simplest, and then we'll go to the cellular case. Okay, and this is much more linked to queuing, as you will see, because these are birth and death processes. And so this is more recent work with Abhishek Sankaraman, a former student of mine at UT. And then Sergey Foss joined, and I will describe these two things for the D2D case. The first model is a point process based. Second is purely queuing based, as you will see. Okay, the setting is again a D2D wireless network. And the tools now will be Markov models. There was nothing really Markov earlier. We'll have Poisson arrivals, we'll have exponential service time. So, I mean, all types of things that queuing theories like. And mathematical machinery is terms of again, point processes, fluid limits, mean field approximations. Okay, so this is the setting. Okay, so here is a artist picture view of the dynamics. Okay, so you have these dipoles that fall from the sky according to a Poisson rain of dipoles, right? So you see them, they are a bit like earlier. They have an orientation, they have a length, an elongation, right? And let's look at this blue one. Okay, so it has this receiver here at Rx. Its transmitter at Tx, and when this dipole comes, it has a file, and I represent the bits of that file in the queue at Tx, right? And the game is that you want to exhaust that queue, all the bits of that queue, according to what Shannon says, right? Namely, if the current configuration at any given time is with the transmitters that you see in the neighborhood. The transmitters which are present at that time interfere, and this interference has to be measured at the receiver. And the instantaneous rate that you get is B times log 2 of 1 plus SINR, okay? Instantaneous SINR, because people will leave, right? So this situation of interference will change. And if the packets or the size of the files to be transferred would be exponential of mean L, the death rate at which this guy disappears, this dipole disappears, would be sort of instantaneous if you see I, B divided by L log 2 of 1 plus SINR at that time, right? So signal is always constant here. The dipole doesn't change its elongation, but interference changes as people join and leave, right? It's a birth and death process of dipoles. Okay, is the model any clear? Okay, so again, please ask if you have any question. Okay, so the stochastic geometry model features a torus, a large torus. The links are these transmitter-receiver pairs. They have as a Poisson rain of intensity lambda. On R represents time times S, right? So it means that there is in space dx at time dt, there is a chance lambda dx dt to see a dipole falling. Each transmitter has a sort of queue with containing an exponential file, file with an exponential size of mean L bits transmit to its intended receiver. And once this file is gone, the guy leaves, right? It's a birth and death process. And at any time, you have hopefully a finite number of links present. And you can represent them, for instance, through their. So here we'll take a simple model where the elongation is almost zero. So the X represent the same time the transmitter and the receiver locations, right? But it's just a simple way of presenting it, right? So why it's a bit too tedious in terms of notation. Okay, interference at locus X for configuring phi will again, there will be no fading in that model. The sum of the 1 over L function, okay, remember L could be R to the beta, for instance. Okay, it's the sum of the received powers. Distance is on the torus, and as we said, the speed of file transfer by link at X in configuring phi is Shannon's formula. So B log to 1 plus, so proportional to log of 1 plus SINR, right? So here, let's take a signal equal to 1 to simplify in terms of power, and you have to evaluate this. N is the thermal noise and B is the bandwidth. Okay, so things which are not so important here, right? And you have the master equation for this dynamics. A point born at XP at time BP with file size LP dies at time DP. And DP is the first time the number of bits you have transmitted, which is nothing else as the integral of the R function at XP over time from BP to T, the first T, such that T is more than BP, such that the integral of the number of bits transmitted exceeds LP, right? This is a master equation. It's unsolvable because, I mean, you don't know the phi U and sort of it's a stochastic differential equation, which is, okay. So it's like this, you can't proceed. And it's, you see already, it's a difficult problem. Okay, and but with these our statistical assumptions, phi t is a Markov process on the space which I devised for that reason at the beginning of counting measures, right? So it's a set of points, finite with no accumulation on these torus, right? So it's a good topological space. You can study this Markov chain, look at existence and uniqueness of stationary regime, and try to characterize the stationary regime if it exists, right? Okay, so you see you are in a completely different framework, although the ingredients are the same. Poisson, now for the arrivals, and Shannon, plus exponentiality for the file size for the death rate. Okay, our main stability results with Abhishek was that if you look at the integral of the L-1 function over the torus, then if lambda exceeds B, the bandwidth divided by log 2 L times A, L is the mean file size, then phi t admits no stationary regime. If lambda is below this B over log 2 LA, and the function L-1 is bounded and monotone, then phi t admits a unique stationary regime. Okay, so necessary condition goes by stochastic intensity arguments. So it's for specialists, I will say a few words about that. Sufficient conditions are queuing, very much queuing-like, and I will go to the queuing results a bit later. It's by a fluid limit. Okay, an immediate corollary of our stability result is that if you take the L function, which is the power law, the one that we used earlier for the examples, then it's always unstable. Whatever the file size, whatever the lambda, it's always unstable, right? So it's linked to this singularity of the L function close to 0. So it has this function, which is not used in practice, leads always to instability. So you need bounded functions, okay, bounded above, right? Okay, the main qualitative result is clustering. So if the point process, so what you have to understand is that the stationary point process of the location of these dipoles is not Poisson any longer. They fall as Poisson from the sky. But intuitively, you see that, I mean, in areas which are very much where there is lots of arrivals, there will be accumulation, right? There will be accumulation. Therefore, interference will increase. Therefore, death will be slower, right? Because death is proportional to SINR, right? Proportional to log of 1 plus SINR, right? So the death rate is a decreasing function of interference, right? Okay, and therefore it will create clustering. The point process in the steady state, if it exists, will be clustered. And so what is clustering? Point process is say clustered if for all bounded positive non-increasing functions f, the short noise f is such that the short noise seen by a typical point of the point process is called the palm of the expectation of short noise, exceeds the value, expected value of the short noise at a typical locus of space, right? So you see, I mean, two mental procedures. The first one, you choose a locus on your torus at random, and you ask what is the difference there. This is the right-hand term, right? Right-hand side. And then you take a point of the point process in the steady state, and you ask what is the interference there. If you take for f the L-1 function, and then it will be more, right? So it's really clustering. I mean, what a typical point, well, you know, pasta, right? Pasta in Poisson point process is exactly the opposite, right? An arrival, a point of the point process sees what time averages see, right? And so this is very different from pasta. A point here, it is true for the arrivals when they are fresh, but in the steady state of phi, a locus of typical locus sees much less interference than the typical point of the point process in steady state, right? So, and the theorem says that the steady state point process, when it exists, is clustered. And so I will show pictures, and I will not give a proof, but this is based on association inequalities. And the key observation is that here, although the dipoles fall from the sky like Poisson, they have a tendency to cluster, right? So in areas where things get bad and where rate is small, Shannon rate is small, when people fall, dipoles fall, they will stay longer. And so it sort of self-sustains. Bad conditions create even worse conditions, right? What is amazing is that for certain rate functions, for lambda small enough, this be stable, right? And we gave the conditions in the theorem with Abhishek, right? And the very interesting observation is that to understand why things are much more complex in this realm is that initially we're giving ourselves geometry, say, oh, it's Poisson, but no, dynamics shapes geometry, and geometry shapes dynamics. Geometry shapes dynamics for the reason that I just explained, right? In areas which are clustered, dynamics, dense dynamics is slower, okay? And dynamics in that sense shape geometry. I mean, in areas which are dense, they tend to be denser, right? So that's a very interesting observation. Let me give a picture. This is a steady state of the, and you see dipoles tend to organize like sort of filaments. Very different. You wouldn't see that for a Poisson point process. And so this is a big challenge to understand that. Currently, the only thing is that we will do is to have heuristics based on mean fields and a method that called the cavity method. We are based on so-called second moment method. Right? So it's a big mystery to try to explain this picture. How this clustering, which is quite visible here, is completely created by Shannon's law and the Poisson rain, right? What it is exactly is a big mystery. We don't know. Okay, so I will skip the proof of instability. It's based on a principle that many queuing theories know, which is called the rate conservation principle, which state that anything which has a steady state, if you take any metric and which is fluctuating, so the rate at which it increases should match the rate at which it decreases, right? Okay, so I could say a few words on that perhaps in the questions, but it requires really machinery which are queuing theoretic type, Campbell theory, PASTA for evaluation of the left-hand side of this RCP, and more fancy things on Palm calculus Papangelus theorem. So it's a bit more technical, right? But so if you massage of that and play with it, you get that that if lambda is more than the lambda c that I gave, then we have instability. So it's purely based on an analysis of this rate conservation principle of King theory, but now for spatial objects, right? So, and as I said, the sufficient condition is based on a fluid analysis, which is Queuing theoretic type, and you all know the fluid theory, which was developed by primarily Sasha Stoliar and Sasha Rybko. So essentially, this is the type of things that we use. So, but so I don't want to enter into proofs. What I want to say more is a few computational results, quantitative results. So I will describe the Poisson or mean field or first order heuristic and the cavity or second order heuristic. And so the aim here is just to evaluate beta f, which is the intensity of the point process of dipoles in steady state. Okay. Okay, so let's go through one of them, perhaps the Poisson heuristic. Okay, let me apply again the rate conservation principle for the bits. Okay. Okay, so how many bits arrive per unit space at any given time? I claim lambda L, okay? L is the mean file size, lambda is the chance to see an arrival here and there, right? Now, what is the rate of decrease of this number of bits, right? And so you look at it again per unit space. So beta is the intensity, a known intensity, and it's a chance to see somebody at the origin, right, around the origin. And then you look at the rate that this guy gets. So log2 of 1 plus SINR, right? Okay. And for that you need to look at really what this guy at 0 gets, and it's clustered, right? Therefore, what this guy gets is less in terms of rate than what the typical locus gets. That's the catch, right? But what you do in the Poisson heuristic, say, oh, let's assume this Poisson, this point process in steady state. We know it's clustered. It's why it's only a first order approximation is Poisson. Then you can remove this so-called palm bias and compute the second term, the right-hand side, in terms of the stationary expectation of the quantity in question, right? And you see that you have to compute the expectation of a log of 1 plus x over y plus a is a constant. There is a closed form expression for that when x and y are independent, and they are in this case. And you end up with the Poisson heuristic, which is an equation in terms of beta f is the unknown, everything else is known, which equates the rate at which the number of bits per unit space increase and decrease, right? And this is the middle equation in blue. And it has a nice shape of a beta f e to the minus beta f times something, which is an integral, like the Lambert function. And you can study that in great detail and find the solution. And this Poisson heuristic is only tight in heavy and light traffic. Okay, so and there is a second order heuristic, which is in terms of indeed this clustering, right? So, and you want to capture this clustering in terms of what is called the second moment measure, which is the chance to see a point at x and a point at y, right? It's the Rho2 function. Okay. And the second order heuristic, which we call also cavity method, says that the density of second order beta s is lambda L divided by log b times log of 1 plus 1 plus 1 over n plus is, where is is the smallest solution of certain fixed point equation, which is given in red here, right? And so you see is on the left, is on the right. And okay, so this is a quite better heuristic. So the rationale is based on conservation for the second moment measure. So it's again a proof form, which is technical, but quite simple actually. The second order is quite good. These are simulation. First order that you see the Poisson heuristic in dash, and almost superpose the second order heuristic and the simulations with their confidence intervals. That's for L of R is R plus 1 to the 4, which is a classical function in the theory. Okay. Let's see, how much time do I have?
Actually, Francois, we should conclude to have some time for the questions.
Okay, so let me say a few words on the interference queuing network, and I will, which is the thing, which is the most queuing theoretic. So this is a vision of it, right? So this is a discretization of space. So you see space and the queues. Okay, so you look at the tagged packet, right, which is in blue here, and you see a collection, infinite collection in the plane of processor sharing queues, and the rate that this blue packet gets is signals to noise, interference plus noise, right? And how do you compute interference in this discrete setting? So you look at guys in your queue, and they interfere with you with rate A0, with a multiplicative factor A0. Those are distance 1 in a graph theoretic distance with A1, blah, blah, blah. Okay, and you get a model with an infinite collection of queues. Arrival in each queue is Poisson. An interference for a queue at distance I is AI. So that's, or you can look at it differently. You number queues in ZD or Z2, and you get AI for the multiplicative factor. And the surface discipline is generalized processor sharing with rate in QI, which is Xi over the sum of AJ Xi minus J, right? Where Xi of t is the state of a QI at time t. So you see, this is the Shannon formula, linearized. So you forget about the log in Z2 now rather than in R2. Okay, so we have extensions with Sergey and Abhishek about the stability. So stability is the same. If lambda is less than 1 over the integral of the A, the network is stable. And this is sharp. And the most interesting thing is, I wanted to conclude with that, is that in that case, in the discrete case, although the dynamic is an extremely complex dynamic, which is infinite dimensional, non-reversible, and it's a particle system, which is made of dependent queues. There is no asymptotic independence. We get a closer expression using the rate conservation principle for the mean queue size, which is lambda A naught over 1 minus lambda integral of the A. Right? So, and the translation of the clustering in the point process is that these Xi are associated, right? Okay, so I will stop here. Let me just say that there was a third last part, but I was not sure I would cover it, which is now dynamics of cellular networks, where we found it's ongoing work, and we found very interesting metastability results using again mean field techniques. Okay, so let me conclude since time is over. So this was this metastability thing. Metastability, just to say, well, is that the system is you're above the stability condition, but the system looks stable for a very long time and then starts diverging, right? So you know these things for Aloha and Ethernet, but they are hold here. And we found quite good explanation for that. Okay, let me conclude for the second part. So now you look at the representation now of time-space interaction in wireless networks. So Shannon and Poisson are still here, and Voronoi also. but you get completely much more difficult results. There is a notion of dynamic capacity, which is not the Shannon one, which involves both queuing and information theory. Usually, these dynamics are neither reversible nor with asymptotic independence. It's why they are very difficult to handle. But we have quite good mean field heuristic in general. And for the first time with Sergei and Abhishek, exact identical results in the low SNR case when we linearize the log. And completely new and unexpected phenomena, metastability, which show up. Okay, so let me stop here, and thank you for your attention.
Thank you, Francois. We are slightly late because the next session begins at 5, but maybe we have time to collect some quick questions from the audience. Is there any question? Well, I will start with one that is probably very easy for you to answer. In the case that the symmetry that your models is broken, for example, because in the communication line there are obstacles or any kind of thing that doesn't make the attenuation of the signal symmetrics in all the direction. I guess that you have to evaluate the integrals numerically because maybe the hopes of having closed forms is small. So how difficult is it to handle these cases?
Yeah, so there are several answers to your question. One is, for instance, if you have random obstacles, right? So, and there is a theory of shadowing, and there are several papers which look at the random shape. You throw random obstacles in addition to the, say, base stations and users, and you want to look at the attenuation created obstacle in addition to the attenuation due to power conservation, right? And so there are several papers on that. Now, if you get a ground with hills and things like that, so then really you have to work out something which is different, which are obstacles which are much more global structure, right? And so there's still a lot of work on that, but it's much more difficult. And in no case of this type, unless you make heuristic approximation independence, I mean, you can get closed form indeed, right? So this is really for flat areas, cities, or but if you have geometric objects which are obstacles, the theory is beautiful. There are stochastic comparison results, and there are a few models where you can compute for vehicular networks or for buildings, in buildings. And so there is a lot of research on that question. It's a beautiful one. But if you take something which is translation invariant, the obstacle, for instance, which are random objects spread out, but translation invariant, cars, I mean, trees, whatever, then there are a few results which are computational.
Okay, thank you. I read a question from Enrico. You mentioned beamformings and other advanced emerging mechanisms. I was wondering whether you considered, in particular, hierarchical cells as appearing in the uptaking 5G standard.
Yeah, so we are working with Nokia Bell Labs with the branch on standards on beamforming. Yes, so it's a very interesting because there are new geometric objects that show up, which are the beams. Okay, and so you have the Voronoi cells, you have the beams, and motion creates new handovers and lots of overhead. And so there is a big activity for 5 and 6G, which are fundamentally relying. And so we have several papers, including one which will come out in transaction wireless, IEEE transaction wireless communication on this beamforming. And so, and we look at the structure where there are several types of the multi-tier, right? With different powers and different radio access technologies with beamforming. It's a very interesting line of thought.
Okay, thank you very much. I think we need to conclude here because the next session is going to begin. So I would like really to thank you, Francois, for the wonderful talk. And I'd like to thank also the audience, and we will meet at the next session of CAST for those of you who want to attend. Bye. Thank you for following.
Bye. Thank you.
Thank you. Just a few words. If you want to follow the quest session, you need to change Zoom room.
Ah, okay.
And,
So
I will close this session and it will reopen with the same link to the Concur
okay.
4 session.
Okay. Thank you very much.
Thanks.